Have you ever just stood outside on a clear night, looked up and felt completely tiny? It's amazing, isn't it? But then you start to think, how are we even seeing those little specks of light? How is it possible to see a star that's trillions of miles away? Well, today we're going to pull back the curtain on the incredible science that lets us do just that.
This is really the core of it all, right? Our eyes are fantastic, but let's be honest, they have their limits. To really, truly see the universe, we have to figure out how to conquer these insane distances, capture light that is unbelievably faint, and in a way, even look back in time. So, how in the world do we pull that off?
To get from our eyeballs to the edge of the cosmos, we need some serious tools. And it turns out it doesn't matter if you're using a little backyard telescope or the Hubble Space Telescope itself. They all have to master three fundamental jobs.
Now, what's really surprising here is the order. We all think telescopes are just for making things look bigger, but magnification? That's actually the very last, and honestly, the least important step. See, first you have to gather enough light to even see the faint object in the first place. Then you have to resolve all that light into a sharp, clear picture, and only then, once you have a bright, crisp image, does it even make sense to magnify it. You get those three things right, and the entire universe just opens up.
But, before we could even dream of building a tool to catch light, we had to figure out what light even is. And that led to one of the biggest questions in the history of science, a question that sounds almost silly to us today. Is the speed of light infinite? Does it just appear everywhere, instantly?
People had tried before. You might have heard about Galileo using lanterns on distant hills to measure its speed. That didn't work out so well. But then this Danish astronomer, Ole Romer, he had a much bigger idea. He wasn't going to use hills, no. He was going to use entire planets.
So, Romer spent years just meticulously timing the eclipses of Jupiter's moons. He figured their orbits should be as predictable as a perfect clock. But they weren't. Sometimes the moons would disappear behind Jupiter a little early, and other times they'd be a little late. Something was off, and he couldn't figure out what.
And this is where he had his stroke of genius. He realized the moon's schedules weren't wrong. His position was changing. You see, as Earth moved to the far side of its orbit from Jupiter, the light from those moons had to travel hundreds of millions of extra miles to reach his telescope. And that extra travel time was causing the delay.
And just by measuring that delay, Romer had done it. He proved light wasn't instantaneous. It had a speed, a finite, though unbelievably fast speed. For the very first time, humanity had a number for one of the most fundamental constants of the universe, about 300,000 kilometers per second.
All right, so now we know light is a physical thing with a measurable speed. The race was on to build bigger and better machines to collect as much of it as possible. This led to the invention of the telescope and two competing ideas for how to build one.
The choice is pretty simple when you boil it down. Are you going to focus light by passing it through something, like a lens? Or are you going to bounce it off of something, like a mirror? Refracting telescopes, think of a classic pirate's spyglass. Use a big lens up at the front. Reflecting telescopes, an idea Isaac Newton really pioneered, use a huge curved mirror at the back.
Now, each design has its trade-offs. Refractors are tough. Their tubes are sealed off from air currents, so you get these really steady images. But, and this is a big but, they suffer from a major flaw called chromatic aberration. Reflectors, on the other hand, don't have this problem at all. And crucially, they can be built to enormous sizes, because a mirror can be supported from the back. That's why today, almost every single major research telescope in the world is a reflector.
You've seen this happen with a prism, right? How it splits white light into a beautiful rainbow? Well, a simple lens does the exact same thing, just a little bit. It causes red light and blue light to focus at slightly different points. And the result is this super frustrating, blurry image with weird color halos around everything. Mirrors, however, they reflect all colors at the exact same angle, so they avoid this problem completely.
So, we figured out how to gather light and focus it without those annoying color fringes. We've built these massive reflecting telescopes. Problem solved, right? Not even close. Because now we have to deal with our biggest obstacle yet, the very air we're breathing.
You know how we all think twinkling stars are so beautiful and romantic? Well, for an astronomer, that twinkle is an absolute nightmare. It's caused by the light from a distant star getting jostled and bounced around by all the turbulent air in our atmosphere. All that constant jiggling is what blurs out the fine details we're trying so desperately to see.
And it gets worse. The atmosphere doesn't just blur our view, it's also like a giant cosmic bouncer.
It blocks most types of light, like X-rays and a lot of the infrared spectrum, from ever reaching the ground. It only leaves a few narrow windows open for things like visible light and radio waves to sneak through.
So, how do you fight back against the sky itself? This is where modern astronomy gets seriously clever. I mean, we've developed some truly incredible technologies to either fix the atmosphere's distortions or just bypass it altogether.
Okay, this is going to sound like science fiction, but it is 100% real. A ground-based telescope shoots a powerful laser up into the atmosphere, creating a tiny, glowing artificial star. A supercomputer then watches how that fake star twinkles and uses that information to make thousands of tiny adjustments per second to the telescope's main mirror, physically bending it to cancel out the distortion in real time. It literally erases the twinkle. It's amazing.
And the final piece of this whole puzzle is how we actually record the light we collect. For decades, astronomers used actual photographic film, but it was incredibly inefficient. It maybe captured 1 out of every 100 photons that hit it. Now, we use digital sensors called CCDs. Think of them like supercharged versions of the sensor in your phone's camera. These things are so sensitive, they can capture more than 90 out of every 100 photons. It's a total game changer, letting us see things that would be completely invisible to film.
So, what does all of this incredible technology actually get us? What's the payoff? Well, let's take a little trip out to the planet Neptune and see for ourselves.
First up, here's what Neptune looks like through a powerful ground-based telescope, but without any of the new tricks. And yeah, it's a fuzzy blue blob. You can tell it's a planet, sure, but there's pretty much no detail at all. This is the full, frustrating effect of that atmospheric blurring.
Okay, now take a look at the same telescope on the same night, but this time we flip the switch on the adaptive optics system, and wow! The difference is just staggering. The blur is gone. We can suddenly see clear cloud bands, even massive storm systems swirling around. And this isn't just about a pretty picture. These details let scientists track weather on a planet billions of miles away.
And finally, here's the ultimate solution. Just get above the atmosphere completely. This is the view from the Hubble Space Telescope. It is perfectly crystal clear because there's no air to look through. This is the sharpest view we can get, the final reward for centuries of human ingenuity.
You know, when you think about it, we've gone from timing moons with a simple clock to building mirrors that can literally change their own shape in real time, all just to get a clearer picture of the universe. And with every single innovation, we've found a cosmos that is more complex and more beautiful than we ever imagined. It really makes you wonder, with the next generation of telescopes already being built, what new wonders are waiting for us, just beyond the edge of what we can see today?